Hello, this is the lecture for exponential functions. All right, what is an exponential function? Well, an exponential function is one that takes the form a times b to the x, where a is some number, and b is the base in an exponential expression that is positive, greater than 0, and not equal to 1. X, then, the exponent, can be any real number. As far as terminology goes, if we had the expression 2 to the third power equals 8, 2 would be considered the base, 3 would be considered the exponent. All right, special note here, when we're referring to exponential functions, if this base, b, is greater than 1, then we have an exponential growth function. If this base here, b, is between 0 and 1, then we have an exponential decay function. All right, we evaluate exponential functions in the same manner that we evaluate any other function. If f of x, the function f, is defined as 2 to the x power, if we are evaluating f of 3, we're simply plugging plugging the 3 into the x and evaluating, right? So f of 3 then is going to be 2 to the third power, or 8. Okay, f of 1, that's going to be 2 to the first power. Of course, that's 2. F of negative 5, well, that'll be 2 to the negative fifth power. And we can't evaluate negative exponents, so we need to change that exponent to positive by rewriting 2 to the negative fifth power as 1 over 2 to the fifth power. And then, of course, 1 over 2 to the fifth power is 1 over 32. Okay. F of 0, that'd be 2 to the 0 power. By the 0 exponent rule, anything raised to the 0 power will evaluate to 1. Okay? When we evaluate exponential functions, we need to make sure that we always follow the order of operations. All right? So if our function f of x is defined as 5 times 3 to the x plus 1 power, f of 2 will be 5 times 3 to the 2 plus 1 power. Now, to evaluate this, we first want to simplify that exponent. So we would write this as 5 times 3 to the third power, of course. And then order of operations, PEMDAS, remember PEMDAS, or that acronym to help remember order of operations, it tells us that the next thing we need to evaluate here is the exponent, right? So this then would become 5 times 3 cubed, or 5 times 27. 3 cubed is 27. And of course, 5 times 27 is, what is that, 135. Okay. What about f of 0? Can I automatically say that's 1? No, because look, my exponent is an expression here. F of 0 is going to be 5 times 3 to the 0 plus 1 power, which of course is 5 times 3 to the first power, or 5 times 3, 15. All right, one special exponential function that we use quite a bit in the sciences, in particular in biology, is the natural exponential function. The natural exponential function is one where the base is Euler's number, or the number e. E, of course, is approximated to 2.718281828, and it goes on indefinitely. It's an irrational number. If we find e in the base of an exponential function, then we know that that is the natural exponential function. We evaluate that in much the same way as we do other exponential functions. If we want to find f of negative 3, we would plug our negative 3 in for the x. So this would then become 7e to the negative 3 if we're dealing with the function here, 7e to the x. All right? 7e to the negative 3 could be written as 7 over e cubed. And oftentimes when we're dealing with e, because it's an irrational number, if we want the exact value, we leave it in that form there with e. If we want a decimal approximation, though, we can find it. 7 divided by e cubed I have my E key on here. I'm going to use my E to the X key. That's a second ln on my computer. So 7 divided by E cubed approximates to 0.3485. It keeps on going. I think I'll just carry 4 decimals here. So I might say that's approximately equal to 0.3485. Okay. F of -1, similarly, well, that would be 7e to the negative first power, or 7 divided by e. Okay, I could type in, if I want a decimal approximation, I could type in 7 divided by e. I can type in 7e to the -1. Wouldn't matter, I could do it either way. Let's do 7e to the -1. I'll use my e to the x key again. Put a -1 up there in the exponent. And the approximate value here, f of -1, is going to be 2.5752 if I approximate to 4 decimals. Okay, how about f of 0? Well, plug that 0 in for x. 7e to the 0 power. What's e to the 0? It's just 1, right? So that's just 7 times 1. Oops, it's 1 or 7. Okay, f of 1, of course, is just 7e to the first power. As an exact value, I would leave that as 7e. If I want my decimal approximation, I'll type in 7 times, let's see, where's my e key? There it is. It's the second key divided by, on my calculator, there it is, 19 point, oh, let's do 4 decimals since we've been 19.0280. Okay, so it's the natural exponential function, just means it has the base e. When we graph exponential functions, we do it in the same manner that we graph other functions, for the most part. We can always just choose some x's and evaluate some y's. So let's sketch the graph of y equals 2 to the x power. Just take a look at that for a minute and see what it looks like. All right, so if we pick some x's, and we're given some here, if x is 3, what is y going to be? It's going to be 2 to the 3rd power, or 2 cubed. That's 8, right? So I can then plot that point when x is 3, y is 8. That'd be this point right up here. Okay, when x is 2, y is 2 to the 2nd power, or 4. So I plot that point, it's right there. When x is 1, y is 2 to the 1st power, or 2. That point goes there. When x is 0, y is 2 to the 0 power. That, of course, is 1. Anything to the 0 power is 1. Okay, when x is -1, 2 to the negative 1st power. That's 1 over 2 to the 1st power, or 1/2, right? So that's about right there. How about x is -2? 2 to the -2, that's 1 over 2 squared, or 1/4. It's getting close to that x-axis, about right there. 2 to the -3rd power, that's 1 over 2 cubed, or 1/8. Getting even closer. What's going to happen as x continues to get smaller? As x continues to get smaller, y is going to continue to get smaller, but it was never going to cross over that x-axis, is it? It won't, because there's no way that I can raise 2 to any exponent and get a negative number for y. So my graph, then, let me connect the points that I plotted. My graph is going to look like this, and it's going to keep on going as indicated by the arrows. Okay. An important thing to notice here with the exponential function is the output, or the value, or the y is never going to get negative. That means we have this horizontal asymptote right here at y equals 0. Right here at y equals 0. We never, ever get a negative value out of an exponential function. Why is that? Why is that? Well, if you look at the format that we have to take for an exponential function, I'll put that page back up there for a minute. If you look at our format, a times b to the x, this b can never be negative. So that means whatever power we're raising that b to, that base, it's still going to be a positive number. It's still going to be a positive number. All right, so there's a graph of an exponential function. Things to note here: we have a horizontal asymptote. We always do with exponential functions. That horizontal asymptote is going to occur right here at y equals 0, unless we shift that function vertically. That can happen. When we do a vertical shift, the asymptote will shift. Okay, and the basic shape of this function is always going to look like this. It's always going to look like this. This is an increasing function. This one here is exponential growth. Right? If the base is different, say the base is 3, right? Say we wanted to graph y equal 3 to the x, right? If we wanted to graph y equal 3 to the x, well, when x is 0, 3 to 0 is 1, y is still 1, so we share this same point here. When x is 1, y is 3 to the first power, or 3. When x is 2, y is 3 squared, or 9. Okay, when x is -1, y is 3 to the negative first, or 1/3, right? Like that. So and so on. So what's going to happen is the basic shape of this graph isn't really going to change. It's still going to look the same. If we have a different base, though, it may make it a little bit, steeper, if you will, or less steep. In fact, the larger the base, the steeper that's going to get. But when that base is greater than 1, 2, 3, 4, 7, 5.5, any of those, you're going to have an increasing function, meaning that as you move left to right across that function, it goes up, right? And we call that exponential growth. Now let's look at some of the specific characteristics in more detail of an exponential graph. Instead of resketching it, maybe I'll just do this, fold this page and put it right over that. What is the domain of that exponential function? Well, it doesn't look like I have any restrictions on x, right? So my domain here would be -infinity to +infinity. What about the range, though? We don't get negative numbers, right? So my range, my y, remember, domain refers to all my x values. Range refers to all my possible y values. Okay, x is left to right. Domain is left to right. Y is down, bottom to top, right, or vertically, or the range would be the smallest, the lowest to the highest. Here we see the lowest is 0, the highest, well, there is no highest. That arrow shows it's going on forever. So my range is 0 to infinity. Do I want to include that 0? Do I want a square bracket or a parenthesis here? I always want to put a parenthesis there because we can never, ever have a y of 0. 2 raised to any power is never going to give us 0, right? Another interesting point to note is the y-intercept. Look at this y-intercept. Let's see, the coordinates of that point, x is 0 and y is 1. And it's the same for both 2 to the x and 3 to the x. If I were to sketch 4 to the x, 5 to the x, and a bunch of others on here, they would all share the same y-intercept. Why is that? Why is that? Well, because when x is our exponent, right? When x is 0, it doesn't matter what the base is. Anything to the 0 power is still going to evaluate to 1. Y is always going to be 1 when x is 0. So my y-intercept is going to be the same. It's going to be 0, 1 for all exponential functions, unless we've got a vertical shift, right, or a horizontal shift. But when they're in their parent form like this, when they're not being shifted, they're going to share that same y-intercept. We have this horizontal asymptote. We already talked about that at y equals 0. I should maybe be like that. Horizontal. And then the graph of 2 to the x, of course, is exponential growth because it is increasing as we move left to right across the graph. Right? Let's compare this graph of 2 to the x with the graph of 1/2 to the x. Here, our base now is between 0 and 1. We should expect to see exponential decay here. Let's plot this real quick. Let's see, when x is 3, y is 1/2 cubed, or 1/8. When x is 2, y is 1/2 squared, or 1/4. When x is 1, y is 1/2 to the first, or just 1/2. When x is 0, of course, 1/2 to the 0 power is 1. Right? When x is -1, 1/2 to the negative first power. What is 1/2 to the negative first power? Look at that, 1/2. Look at that for a minute. 1/2 to the negative first power. Well, to evaluate that, I need to get rid of that negative, right? So move it to the dividing line. This becomes 1 over 1/2. What is 1 over 1/2? Well, that's 2 over 1, or just 2, right? So then 1/2 to the negative second power, that's going to be 1 over 1/4, 4. And 1/2 to the negative third power, that'd be 1 over 2 cubed, or 1 over 1/8, or 8. Right? Let's plot those points real quick. When x is negative 3, y is 8. That's right there. Then there's 4, 2, 1. Then we got 1/2, 1/4, 1/8, and so on. If I connect my points and continue with the pattern, my graph is going to look like this. There's my graph of 1/2 to the x power. 1/2 to the x power. Okay, I still have my asymptotes the same. Look at this. We still never get a negative y, right? Because our base is positive still, it's just small. But we now have a decreasing function. Look, compare that to 2 to the x. Oops, I'm not showing, let's move that over. Compare my 1/2 to the x to my 2 to the x. They are reflections across the line y equal x, aren't they? The most important point here, though, is when your base is greater than 1, you have an increasing function. That's exponential growth. When your base is between 0 and 1, you have a decreasing function. That's exponential decay. All right, let's look at the characteristics a little bit more closely. Let me fold my graph in half so I can have it all over that. The graph of 1/2 to the x, what's the domain? Same as 2 to the x, right? Negative infinity to positive infinity. We have no restrictions on the x, left to right. The arrows are indicating that goes on forever. This arrow goes up, but it also goes to the left. Okay, the range looks like that's the same as well, 0 to infinity. Same as 2 to x. The y-intercept, and the same y-intercept, that's that nature of having an exponent of 0, right? So my y-intercept is the same, 0, 1. My horizontal asymptote doesn't change either. Horizontal asymptote is always y equals 0. The only difference when this base is 1/2 versus 2 is that we're now looking at exponential decay. We're now looking at exponential decay. All right. So when we're graphing exponential functions, we can do it by picking x's and finding y's and sketching the graph. But since we know the basic shape and we know the characteristics of exponential functions, it can be a little bit easier by just picking a couple of points and then filling in the rest, right? So here we have an exponential function in its full form. Before we were looking at, remember our form for this function, f of x or y equals a times b to the x, right? The previous examples, a was 1. Well, what happens when a isn't 1? Look at this one here, y equals 3 times 2 to the x power. Well, we know from transformations that this would be the graph of 2 to the x stretched vertically by a factor of 3, right? So when we think about it. But because of the nature of exponential functions, we can always graph an exponential function that isn't being shifted around by plotting its vertical intercept and one other point. Okay, the vertical intercept, that always occurs when x equals 0, right, on the vertical axis. The one other point, the easiest one to deal with is when x equals 1, right? If x equals 0, y is 3 times 2 to the 0 power, which of course is 3 times 1, or 3. Okay, so there's that point. When x is 1, y is 3 times 2 to the first power, or 3 times 2, which is 6. So when x is 1, y is 6. That's going to be right there. Okay, I really only need those 2 points because I don't have any vertical shifting, so my asymptote is the same, right? Here it is. My asymptote is still at y equals 0. My base is 2. That means this is an increasing function. So I know this is going to look something like this. Right? I know that that's what that graph's going to look like. And if I want to be real exact about this part right here, I could pick another value. I could say when x is -1, y is 1/3. So actually, I didn't probably scoop this down enough. Oh, no, it's 1 actually, not 1/3. Yeah. So it probably should look more like that. But it's really not hard to graph with just the y-intercept and one other point because we know these characteristics of an exponential function. Okay. Now, transformations do come into play. Sometimes we have exponential functions that are shifted, right? They're shifted. We can shift a function up here when this first one, f of x is 2x plus 5. If we're shifting up, we're just adding some number of units out to the end. This will be shifted up 5 units. If we subtract 5, we're shifting down 5 units, right? Remember, up. When we add to the end, we shift up. Remember that when we subtract from the end, we shift down, okay? And we can also add and subtract up there in the exponent. If we add 3, for example, in the exponent, it's counterintuitive. When you add, the x is getting bigger, you want to think you're shifting right. It's counterintuitive, though. When you add up there in the exponent, or when you add to the x, you shift left. You actually shift left. It's counterintuitive. When you subtract up there in the exponent, you shift right. Counterintuitive again. 2 other transformations that we often see is when we stick a negative out front, we make our whole function negative. We're reflecting it over the x-axis, or we're just doing a flip. All of our positive y's become negative down here, so we flip the thing. And when all of our x's become negative, as in 2 to the negative x, we're shifting over the y-axis, right? I'm not shifting, I'm sorry, reflecting over the y-axis. We're doing a flip over the y-axis. All right, let's look at a few examples. Graphing with transformations. Say I wanted to graph y equals 3 times 2 to the x minus 2 by starting with the parent function y equals 3 times 2 to the x and then applying the transformation. Well, we already did graph y equals 3 times 2 to the x. We'll do it with the vertical intercept on one other point. The vertical intercept happens when x is 0. So 3 times 2 to the 0 is 3 times 1, right? So 0, 1, I'm sorry, 0, 3 is on there. And when x is 1, 3 times 2 to the first, 3 times that's 6. I might do when x is -1, 2, just to see that's, so 3 times 2 to the -1, that's going to be 3 halves. About right there, just to make it a little bit more. Okay, so here's our parent function here without the transformation, right? This black one that I drew, we do still have that horizontal intercept. Put that, there's our horizontal intercept. Okay, so my black guy here is the parent, or y equals 3 times 2 to the x. Now we want to shift it down too. Well, we want to start by shifting. If we're going to graph 3 times 2 to the x minus 2, right? We're going to graph that guy. We're just going to shift everything down too. So our horizontal asymptote goes down too. Okay, and then our points that we plotted, our vertical intercept goes down too. The other points we plotted, they move down 2 units. And now our purple graph here, our purple graph is y equals 3 times 2 to the x minus 2. Okay, and just graph that parent function and then shift, oops, minus 2. And my mouth got disconnected there for a minute. We just graphed the parent function 3 times 2 to the x and shifted it down 2 units. Okay, let's look at a couple more examples. What if we wanted to graph -2 to the x or m2 to the x plus 1? Well, we should start with the parent function, right? 2 to the x. Let's graph that real quick. Y equals 2 to the x. It's going to have its asymptote right here. There's no for the parent. The intercept, of course, is going to be at 1, 0. One other point would be when x is 1, y is 2 to the first, or 2. I might even put a few more points on just to be more accurate. 2 squared and 2 cubed. So there's the parent function in black. That's my y equals 2 to the x. Okay, if I'm reflecting it, right, or say I want to graph y equals negative 2 to the x, I'm making the whole function negative. So all the y's that are positive up here are becoming negative. We're going to reflect that whole graph across the x-axis, right? So when x was 0, 2 to the 0 was 1. Well, now it's negative 1 down here. When x is 1 and y was 2 is up here. Well, now it's negative 2. It goes down here. Negative 4 here, the 8 here. The whole thing is just going to be reflected. Okay. How about y equal to the x plus 1? Here, we're starting with that same parent, the black graph y equal to the x, but we're adding 1 up there with the x, right? That means we're going to do what? We're shifting, right? Which way are we shifting? We're shifting left 1 unit. Shifting left 1, right? So we just, key points here that we plotted, we just shift them all to the left 1. And now our blue graph here, blue graph is y equals 2 to the x plus 1. Okay, transformations can be very helpful when we're graphing exponential functions. All right, let's talk just for a minute about writing exponential functions. We saw that the standard form for the exponential function is f of x equals a times b to the x, all right? Well, think about that a for a minute. Well, when x is 0, right, that's our starting point for any function, right? B to the 0 is just going to be 1, right? B to the 0, that doesn't matter what that base is, but it's still going to be 1. So that means a is going to be our initial value of our function. A is our initial value, all right? And the base, we can think of the base as 1 plus r, where r is the rate of change. So our base is going to be 1 plus the rate of change. Okay, so look at this table here. Given the initial values and the rate of change, can we write an exponential function for these? Of course. If the initial value is 101, the initial value is our a, right? So that means our function here is going to be a. If our format is this, f of x equals a times b to the x, right? Our initial function, our initial value is a, so f of x would be 101 times, and my growth rate here is 14%, so my a is going to be 1 plus 14%. Of course, we always move the decimal over 2 places when calculating with percentages, so it'd be 1 plus 0.14 to the x power, or 101 times 1.14 to the x. Okay, what if the growth rate is only 3%? 3%. We got to move that decimal over 2 places. Oh, we're going to need 0 there as a placeholder, right? That means my function is going to be my initial value, this time it's 86, times 1 plus 0.03 to the x power, or 86 times 1.03 to the x. Okay, what if the growth rate is 113%? Wow, that's a big growth rate, right? Well, here's our decimal. Move it over 2 places. So it's 1.13. 113% is 1.13 as a decimal. Well, if our initial value is 65, okay, and our base is 1 plus the rate of change, is going to be 1 plus 1.13 to the x power, or 65 times 1 plus 1.13, that's 2.13 to the x power. Okay, what about decay rates? Decay, remember that's going to be a decreasing function. That means that base has to be between 0 and 1. If we're decaying, we want to subtract that rate of change from 1. All right, so if our initial value is 119 and we have a decay rate of 9%, then B, my base here, is going to be 1 minus 0.09 to the x power, or 0.91 to the x power. 119 times 0.91 to the x power. Okay, if the decay rate is only 0.8%, let's think about that for a minute. I'm going to move that decimal over 2 places, and you know the 0 is a placeholder there, right? This means that this function, my initial value is 125 times 1 minus, not 0.8, but 0.008 to the x power, which of course would be 125 times 0.992 to the x power. All right, so the base in the exponential function reflects the rate of change. It reflects the rate of change. If it's a growth rate, you add that rate of change to 1. If it's a decay rate, you subtract that rate of change from 1. All right, let's see if we can use an exponential model here. We have this equation, y equals 901 times 1.032 raised to the t power. And this equation models the number of students in a certain state that go to out-of-state colleges or universities each year from the years 1996 through 2003. Y is representing the number of students that study out of state. T is the number of years after 1996. All right. If we can assume this model remains constant, or remains true, this model remains true, then can we use it to estimate the number of students that studied out of state in the year 2010? Yeah, I think we can, right? This model applies the t is our exponent now. The t in this model, this represents the number of years since 1996. So if we want to know 2010, we want to subtract 1996 from it, and we see that the year 2010 is 14 years after 1996. So we want to put 14 in for the t. So then y, or my number of students, is going to be 901 times 1.032 to the 14th power. Right? Let's get a calculator and see what that evaluates to. Let's see, 901 times 1.032 raised to the 14th power. My caret, get up in that exponent, right? It looks like this is 1400.36. Well, can I have 0.36 students? No, so I better not put a decimal in there, right? This is just going to be 1400 students. Can't have 0.36 of a student. That doesn't make sense. How about in the year 2023? The same thing. 2023 minus the 1996 is going to be, was it 27 years? So then y would be 901 times 1.032 to the 27th power. Let's see what that is. 901 times 1.032 raised to the 27th power, 2,109 students. Is this an exponential growth or an exponential decay model? Clearly, the output of the function is growing, right? It's exponential growth, getting bigger, right? Also, that base is greater than 1, so I should expect it to be exponential growth. What is the growth rate here? Well, it's 1.032, right? So it's 1 plus 0.032. There's my growth rate, 0.032, or 3.2% if I write it as a percentage. Okay. Another exponential growth model that is very common is the model that's used for compound interest. Okay, compound interest is when a bank pays you interest on the interest if you have an investment, or it's when you pay someone interest on the interest when you have a loan. All right, the formula for compound interest says that some future amount is equal to the principal value, that's the initial value, times 1 plus the rate R over N, where R is the rate of interest and N is the number of times per year that interest is compounded, right? And then we raise that to the NT power, where T is the amount of time that an investment stands in years. Okay? So look, it's an exponential model, right? Just written a little differently, right? Our normal, let's see, let's put our standard form for the exponential function. F of x equals a b to the x power, right? Look, our base here, 1 plus the rate, plus the growth rate. But if we're doing it more than once a year, that's where this compounding period comes in, the number of times that we compound per year. Okay, and then we raise it to not just the number of years, but the number of years times how many times we're going to compound in that year. All right, so to use this model, let's look at some examples here. If $14,300 is invested at an interest rate of 8% per year, right, and we calculate with that, that's going to be 0.08, move that decimal over. Okay, find the value of the investment at the end of 5 years. All right, so our T is 5 years there. Okay, and of course to the nearest cent because it's money. All right, if it's being compounded annually, what is my principal amount? Well, there it is. My principal amount is at $14,300 that I had initially. So if I'm only compounding annual once per year, my future value, my A, is going to be that principal amount, $14,300 times 1 plus my interest rate of 0.08 divided by how many times am I compounding per year? If it's annually, I'm only compounding once per year. Divided by 1, raised to the 1 times, and T here is 5, 1 times 5 power, right? So annual compounding is kind of like simple interest, isn't it? But let's see what, for 1 year anyway, let's see what this is after 5 years. Let's see, so we have our principal amount, our $14,300 times 1 plus my rate of interest divided by 1. I don't even really need to do that, but I'm going to type everything in, right? And then raise, let's use the caret key, raise to the 1 times 5 power. We see that after 5 years, if I only compound annually, the $14,300 has grown to $21,011.39. Okay, what do you think would happen if we started compounding semi-annually? That'd be twice per year, right? With annually, compound once per year. Semi-annually, we're going to compound twice per year. So we're going to be earning interest on interest, and we're going to calculate that 2 times per year instead of once per year. So am I going to have more or less money at the end of the 5 years? Well, let's find out. Semi-annually, this is going to be $14,300, my initial value, my principal amount, times 1 plus the interest rate of 0.08 divided by 2 this time. So we're going to compound it twice per year. Raised to the 2t power, 2 times 5 power. Right? Stick that in the calculator and see what that is. 14,300 times 1 plus 0.08 divided by 2 raised to the 2 times 5 power, or 10 power, $21,167.49. It is more money, as expected. I don't know if you expected it, but if you compound more often, at the end, you're going to have more money because there's more interest earning interest, right? You're calculating that interest and putting it back in there with the principal more often, right? So $21,167.49. If we compound monthly, this is the most common compounding, I think. Mortgages and car loans are often compounded monthly. what's my n going to be if I'm compounded monthly? There's 12 months in a year, so my n would be 12, right? So my amount here is going to be that $14,300, that principal amount, that initial value, times 1 plus the interest rate of 0.08 divided by the compounding period. Here it's 12, raised to the nt power, that's 12 times 5 power. Okay, let's see if the calculator will tell us what that value is. Should be more than the 21,167, right? Because now we're compounding it 12 times per year instead of just 2 times per year. Let's see. 14,300 times 1 plus 0.08 divided by 12 raised to 12 times 5, or 60th power, $21,304.79. So after 5 years, the more often I compound, the more money I have in that bank account. What about daily? Here, well, let's say there's 365 days in a year. So if we compounded daily, my n would be 365. And my future value, my a, is going to be $14,300 times 1 plus 0.08 divided by 365 raised to the 365 times 5 power. Let's see what that is. 14,300 times 1 plus 0.08 divided by 365 raised to the 365 times 5 power. And there we have it, $21,332.16. That's our highest amount there. All right. And if for some reason we compounded twice per day or hourly, this amount would keep going up. It would keep going up. This is an exponential growth function, right? So occasionally we see you see an investment that is compounded continuously. If we compound continuously, we have to use Euler's number as the base, or E as the base. The formula for calculating continuously compound interest is A equals P, that principal amount, times E, that's Euler's number, 2.7, et cetera, raised to that interest rate times the number of years. All right. So if we have that same $14,300 at that same interest rate of 8% per year, okay, we're investing it for that same 5 years, but we're compounding continuously, we should get even more than we did when we compounded daily, 21,332. Let's find out. That future value is going to be that principal amount, 14,300 times E raised to the R, that's 0.08, times T, that's 5. Mr. Calculator, tell us what that is, please. 14,300 times E, I'll use my EVX key. E raised to the 0.08 times 5, and the amount that we would have at the end of the 5 years is $21,333.09. So not a ton, a lot more, but definitely the highest value that we get is when we do continuous compounding. All right, that ends the lecture on exponential functions.